Today we're going to talk about the scientific revolution of the 1600s, which really dealt with how our early views of the universe changed. Now, it starts with Aristotle, lived about in the early 300 BC. He was an ancient philosopher, and one of the things that he stated was that the Earth was at the center of the universe, and everything moved around the Earth on perfect circles. And this view of the universe was adopted by the prevailing religions at the time because it followed what they said. So it was held on by a lot of people until really the 1600s. So almost 2,000 years this viewpoint was held on to. And his model placed the heavy, crass, movable Earth at the center of the universe and everything moving around it on circles. And then the farthest circle were all the stars, and they called this a celestial sphere. Now, this meant that all the stars were the same distance away, which they aren't. They are different distances away, and things don't move around circles on the Earth. Nothing moves around a circle on the Earth. Now, one of the things that really showed a flaw with the Aristotle view of the universe was that certain objects kind of seemed to backtrack throughout the month. For example, this is a picture of Mars. And if we looked at Mars throughout the month, we would see it would be moving forward, but then all of a sudden going backwards for some days, and then going forward again. Well, this was called a wanderer. Or the term for wanderers back then was planets. So that's actually what came up with that term. But this showed that, well, if everything moves on circles around the Earth, there's no way it could just go backwards. So the Aristotle view had to be kind of altered. And so that brings along Ptolemy. Ptolemy was a mathematician. He developed a way to make the Aristotle viewpoint of the universe fit some of the motions. He placed still everything going around the Earth. The Earth is in the center, but everything moved around circles around the Earth. And sometimes they moved around a circle on a circle. So like Mars out here, it would move around this circle as this whole circle moved on a circle. And so this would explain the backwards motion that we would see from time to time. So Ptolemy tried to make more sense of this, but as our observations became more and more detailed, we noticed that there were still some issues with this. But it really wasn't to Nicolaus Copernicus in the early 1500s for someone really to give an opposing viewpoint. And Copernicus came up with the, of course, called Copernican model, which placed the sun at the center and everything moving around the sun on circles. Again, the circle here is the downfall because it's not the true shape, but this did make it easier to explain some of the motions. But the problem was that this was considered heresy, and pretty much no one was allowed to talk about this in Italy, where Copernicus was from. And one of his followers, Galileo Galilei, who's really one of the greatest scientists of all time, one of the first scientists, followed his viewpoint and tried to provide evidence for it. Galileo was an Italian physicist, mathematician, and astronomer, and he really changed the way science was done, the way people perceived the sky and the objects contained. And one of the ways he did this was by using a telescope. He was one of the first major scientists to use a telescope to look at the night sky. And there were various things that he noticed. I mean, he first looked at the moon because it's one of the biggest objects in our sky, and he mapped out the surface of the moon. And he noticed there were high points, low points. It wasn't a perfect surface. And that went against a lot of people's viewpoint that, well, the moon has to be perfect because it's in the sky. One thing you also noticed that there were, when you looked at Jupiter, there were 4 little pinpoints of light around Jupiter. And these kept changing position. They just stayed around Jupiter, though. Well, they're moons. They're moons of Jupiter. And they're actually called the Galilean moons. Io, Europa, Ganymede, and Callisto. We'll talk more about those later. And again, we have the Galilean map of the moon, which showed the imperfections, which looked a lot like the Earth's surface. And I know we just talked about phases of the moon, but these are actually the phases of Venus. Venus being a planet closer to the sun than us. He noticed how it went through a set of phases, and that could only happen if it was not going around us, but going around the sun. And so he really gave a lot of evidence for it. But his work alone would not really support the Copernican system. We actually need to rely on a couple other people. One of those was Tycho Brahe. Tycho Brahe was a Danish nobleman known for his comprehensive and accurate astronomical data. He had a whole island set up with very large mechanical instruments used for measuring the motion of objects in the night sky. This is all done with the naked eye. No telescope was used, but his data was the most accurate data up to that point, and it could really help someone try to figure out the true nature of the universe if they could use his data. But Tycho followed a sort of Aristotle view. He still placed the sun at the center, but he placed the Earth going around the sun. Well, he placed the Earth at the center, everything going around the Earth, but then things also going around the sun as it went around the Earth. It was a very complex system. It could not be made to fit. But Tycho Brahe needed a mathematician who could make sense of all of his elaborate data that he had. And this is a drawing of some of the instruments they had. I mean, you think building-sized instruments for measuring the motion of the objects in the sky. Tycho Brahe needed Johannes Kepler. Johannes Kepler was a mathematician. He had his own viewpoint for how the universe would work. He thought that the universe would have to follow geometric laws. And he, while working for Tycho Brahe, was forced to try to make Brahe's model fit the data, or really the data fit the model. Tycho Brahe died early on. It was actually an interesting story. We'll get to that later. Left the data to Kepler. Kepler, then looking at the data after a long time, finally figured out the true path that objects take, and that is that planets move in elliptical orbits around the sun in this elliptical shape. And now an ellipse is not a circle, whereas a circle has one center point and everything is the same distance away from that center point. We call that the radius. An ellipse has two center points, and everything is the same distance away from those two center points at any point on the outside. Those are always the same. So this is a very specific mathematical shape, but it fits. Now all of a sudden we have a model for how our solar system works. The sun is at the center. Everything moves on elliptical orbits around the sun, which was not how he originally viewed it, but he did look at the data and he looked at the evidence, and the evidence pointed to the ellipses. He came up with 3 laws of planetary motion. First is that planets move in ellipses. Second, the closer you are to the sun, the faster you travel. And the third, that the time it takes for one trip around the sun squared equals the average distance away from the sun cubed. So that's actually like period squared equals how many astronomical units away cubed. An astronomical unit is equal to the distance between the Earth and the sun. This is a picture showing the elliptical orbits of the planets and other objects. And some of these orbits are very close to a circle, but they aren't. They are an ellipse. They're just, the two center points are very close together. Our orbit's kind of like that. We're just somewhat elliptical, which means we get closer and farther away from the sun. And of course, remember from last unit, in January, we are the closest. July, we are the farthest. That's because our orbit is elliptical. So